In the next two videos, we're going to talk about estimating the volume of a volcano like Mount Fuji. Um, it has a circular symmetry looking down on it. It's basically circular in shape. And we could think of the volume as we have before with areas. Except in this case, instead of rectangles, we could think of these as being disks with radii that vary in such a way that they outline the shape of the volcano. So we'd have a stack of disks as shown here, and we'd sum them all up. So in a discrete sense, we'd have a volume, which would be the sum of the volumes of each of these disks from the base at some elevation all the way to the top of the volcanic cone up into the caldera here. So we have, in a discrete sense, those disks are going to have an area, which is pi r sub I squared, where r sub I is, is going to be the radius of each of these individual disks, and it will vary from disk to disk. And then a continuous fashion, this summation turns into an integration from some minimum elevation to a maximum elevation. We still have the area of individual disks here. I could remove this I. It's not needed in this case, but we do need to have r expressed as a function of z, or vice versa. We need to have some common variable of integration. So we have to define r as some function of the volcano's height. So in this integral formulation, we're showing it more the way we would go about it, where r is a function of z, and we have the area of individual disks as pi r of z squared over the volume, over the step dz, infinitesimally small step dz. So first what we're going to do is we're going to talk about volumes of revolution, and we're going to use that approach to, well, we'll compare this on the next video to see if it really provides a very good estimate of the volume of a volcano. But we're going to determine the volume of a cone which opens outward along the x-axis, and then we're going to do it again. We're going to stand it on end so that the cone opens vertically downward along the y-axis, and so that it looks kind of like a volcano in that sense. So we're going to start with this object here. It opens up out along the x-axis, and we can think of these volumes of revolution as, you have an object which has some, or a function which has some shape. In this case we have a straight line. Could have indicated that it goes from 0 to some x max, let's say. So it defines a triangle. And the idea of volumes of revolution is that we rotate these volumes about, we rotate these areas about the x-axis, and we sweep out circles. So the circles are going to have variable radii, which decrease towards the apex of the cone. So the volume is generated by the area of a variable circle moving with its plane perpendicular to the axis of revolution. So over here, the differential volume element is going to be pi r of x squared, or pi y of x squared. So r is going to be some value of y, which is going to be variable along the axis of the cone. And in this case, y of x is going to vary with the slope of the hypotenuse, or as r is to h. So We could say that y is to x, this value of x, as r is to h, or that y is equal to r times x over h. So that the differential volume element then is going to be pi, basically this quantity, y squared, we've got our y squared here, pi, r over h, x squared dx. And the volume integral then would be, in this case, integrating from 0 to h. We're coming out along the length of the cone, integrating those volume elements from 0 to h. And when we evaluate this integral, this is something that you should be able to do. You'll find that, well, of course, we're really just integrating this term. All these are constants. We could, just pull those out. So the integral of x squared is x squared dx is going to be x cubed over 3. So we have our x cubed here and our 3 down here. And it's a definite integral, so we're going to evaluate it from 0 to h, which gives us an integral of pi over 3 times r squared h. And so that would be the volume of this cone. So to turn the cone so that it looks a little bit more like a volume, we could do the same thing, except we're going to have the cone sitting on the x-axis. So x then corresponds to the radius, and it's a function of y. So otherwise the problem is the same. We have x of y is equal to the radius of a disk, so we have x of y here, and it will vary in proportion to h minus y. So we basically come down from the apex here, so we have to subtract y from the height of the cone. But x increases in proportion to h minus y times r over h again. So we have r over h. And so that gives us x is equal to h minus y times r over h, and dx is going to be equal to minus r over h dy. So we have a minus sign in there that pops in. And we're kind of looking down on these individual disks over here, and they have area pi x squared, which is defined by this function over here. So just kind of running through the equations, then we have the volume of the cone, just the area dy. We're integrating that, but we're integrating in this case from h to 0, so we're coming down from the top of the cone. And then we substitute in for r squared in this case, which is our x of y, which is h minus y times r over h, and then we're squaring that. And so this is pi r squared. This is just the area of an individual slice, an infinitesimally thick slice in the dy direction here. So that's our basic integral. And then over here we go through the integration process. So we have this minus pi r squared over h squared, integrating from h to 0 of h minus y squared dy. And that gives us, again, just using our power rule relationship, it's a two-step process. It's a chain rule here, so the minus signs, this minus sign that we had here cancels out. Because when we differentiate the inside term here, we get a minus sign. So a minus times a minus. And then we're integrating or evaluating this definite integral from h to 0. It's equal to 1/3 pi r squared h. And so finally, just an example using this equation, if we have a volcano which is 3.5 kilometers high and has a base of 20 kilometers, then we get a volume, evaluating this expression here, as 1,466 cubic kilometers. So is that a reasonable estimate of a stratovolcano's volume? So we can also take a discrete computation approach. We've done this, in several of our examples. We've already defined what x is, and And we know that the area of an individual disk would, let's say disk sub I, would be equal to pi r sub I squared. And the volume of that disk would just be pi r sub I squared times delta y, the thickness of this disk. Okay, so the volume then is easily evaluated, let's say in Excel, just as pi times the sum from I equal 1 to however many disks it takes that are delta y thick in order to go from the base to the top of the volcano, or the top of the cone in this case. So we're integrating this r squared delta y, basically this formula here, in order to get the volume. And so here we have, if we assume that we have a base that has a radius of 20 kilometers, extending out in this direction or this direction, and extends from 0.2 kilometers to 3.73 kilometers. Over here I've just kind of shown the Excel computation. And over here I've shown the exact integration, the result from the definite evaluation of the definite integral. Over here we get 1324.5 cubic kilometers. And down here we get 1,416 cubic kilometers. So two different approaches. They yield similar. Their differences are less than 10%. Estimates of the volume of these volcanoes agree within about 90 cubic kilometers or so. So we're using pretty thick disks, 0.1 kilometer or 100 meter thick disks, and so we get a couple different answers, but similar, not order of magnitude differences. So the next time we're going to talk about, we'll use Mount Fuji as an example, and we'll talk about approaches for estimating the volume of Mount Fuji. Is that volume, we do have this, we'll be working with about this range of elevations, with the radius, the basal radius going out about 20 kilometers. So is the volume of Mount Fuji, based on this profile, which is taken from Google Earth, is it going to be, is the cone a good approximation of the volume of the volume of Mount Fuji? So we'll think about that a little bit, and then we'll come back to this next time. See you then.